two-particle harmonic oscillator, pretty much the same idea. Okay? If the potential energy of interaction between the two particles is 1/2 kx squared, okay, that means the force between them is minus kx, okay, where x is equal to x2 minus x1, the relative coordinates, Hooke's law, okay. So it's like you have two particles that are connected by a spring. Simple harmonic motion, okay. Your relative motion, if we just restrict this to one dimension, would just be vibration. Okay, if we restrict this problem to just one dimension, then the movement of the two particles would lead to basically spring-like motion, right? So the relative energy of the two would be called the vibrational energy. All right, so the classical description is that the total energy would just be whatever the translational energy is, the movement of the two particles as a whole, as tracked through the center of mass, plus the vibrational energy. Now, the frequency of the vibration will just be the same formula you had before. Frequency is 1/2 pi squared of k, but instead of dividing that by the mass, we're going to use the reduced mass. Okay, so the frequency is 1/2 pi squared of k over mu. These are all still fresh in your mind from the test? Okay, so that's your vibrational frequency, the classical frequency of vibration. Quantum mechanical description, same deal. When you solve the problem, you essentially get a harmonic oscillator problem for a particle that has a mass equal to mu. Okay, so you get the same wave functions, same allowed energies. The vibrational energies would be v plus 1/2 times h nu, where the quantum number v is restricted to 0, 1, 2, 3, and so on. But keep in mind this nu right here, this frequency, you have to solve it in terms of the reduced mass, not the actual mass, because you have two masses there.